Okay, folks. Sorry I'm not here today, but you get a sweet video of me going through the last things that you need to know for this entire semester. So this is the end of your notes. We so far have learned how to determine the rate law, right? The equation that helps us figure out how fast or slow a reaction is going. And we've done that with these graphs, or these, not graphs, well, these graphs. This chart can help us figure that out, right? If I get data from an experiment, if I have graphs from an experiment, I can figure out if I have a first, second, or zero order reaction. And finally, if we have a little bit of information and we have a true understanding of what the reaction is doing, we can start to use this thing called mechanics. So here is what we still have to do the reaction, but if there is a multi-step reaction, we can use mechanics to help us figure out the rate of the reaction. And this is useful when there are a series of elementary steps. So elementary steps. So what happens is, in all the reactions we've looked at so far, your reactants turn into products, and that's over. The reaction is done. Now, that's not always true. There are some reactions that, as you start to make products, then those products start to react, and then as that reaction happens, there's more products, and those products start to react until you finally get to the end of a reaction. And so, as we can see here, we have a three-step reaction. We started by just mixing A and B together, and we got X, but X actually started to react with some of the extra B, and then we got Y. And then Y, well, there must have been some C in our initial beaker, so Y reacted with C, and we ended up with D and E, right? So if I think about this, my reactants over here, reactants are for reactants, I started with A and B, it made X, so there's some A and B in here, and then X was produced, so that's not what I started with, B, and then I started with some C, right? So I had A, B, and C. At some point, I produced X and Y. Those like showed up for a little while. But then finally, at the end, at the very end, I ended up with just D and E for my products. So kind of break that down a little bit and see that's what's happening in our beaker. I started with A, B, and C. I produced some X and Y, but then I ended with D and E. So it looks confusing. There's multiple steps, multiple reactions going on inside of your little experiment. But if you know the three reactions that are taking place, then you can determine the overall reaction. So the overall reaction, I like to make a line going through my arrows, kind of like in math class, like you split your beginning of your equation with your end of your equation. And then I'm going to cancel out anything that is on both sides. So if I look for A here, there's no A's here, so it gets to stay. B, no B's here, so it gets to stay. But X, I have X on both sides, so I get to cancel it out. Y, I have Y on both sides, so I get to cancel it out. C, D, and E have to stay. So now we're going to look at what is the overall reaction. Well, I started with 1A, and I still have 1A. I have 2 B's, so when I count for both of them, so I have 2 B's plus 1 C, and that is going to produce 1 D and 1 E. Cool. So there's our overall reaction. We had these things called intermediates. Intermediates, that was my X and my Y from above. These are any molecules that are canceled out in our reaction. They are essentially produced and then reacted, right? X was produced, then it was reacted, and now it's gone. Y was produced, then it was reacted, and now it's gone. So that's what we see here, X and Y, X and Y. These are never going to be in your final reaction. Never in overall reaction. Reaction. Huh, okay. I was about to write that shorthanded and then I didn't. So that's a C. And then we also have catalysts. So you might see a catalyst, right? We put a catalyst in a reaction to make it go faster, but it's not truly a part of the chemical reaction. It's just there to help A and B find each other, right? It's like the Tinder of chemical reactions, right? So like the little dating app. Like, oh, there's 2 chemicals out there, they want to react. The catalyst, right? Tinder will help them find each other so that they can make X. So catalyst is going to be present, but at the end, right? If A and B find each other and fall in love, Tinder doesn't get to stay with them forever, right? They get rid of Tinder. So that's like your catalyst. It's there, but then it's not actually there. So it's present at the beginning and at the end. And that's how you'll know that it's a catalyst, because you'll see it at the very start and you'll see it at the very end, right? Here's my starting zone. Here's my end. So if I have like a M and an M in both of these, then I know that that must have been a catalyst, and I get to also never use it in my overall reaction. So I'm also going to ignore it, okay? So never use that in your overall reactions. That's true for both of those. So here is some practice. We'll do one together. We have determined the following in the diagram to the right. So we have pictures instead of A, B's, and C's. We want to know what are the reactants. So let's see. We're dealing with we have O3, so this is ozone here, O3, and it's reacting with a Cl. This is Cl. And it's turning into O2, and we have OCl. And then over here, OCl creates more ozone, O3, and then I end up with a chlorine and an O2 and an O2. Okay, so if we take a look at this, what do we get to cancel out? Remember, we get to separate on our lines here, and it looks like on both sides I have an OCl and an OCl. And so all my reactants, looks like my reactants are O3 and Cl and O3 again. So my reactants are going to be ozone and chlorine. All right, the products, well, I'm ending with oxygen, 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 and a chlorine. So my products are O2 and a chlorine. Oh, I guess I have to cancel that out, huh? So chlorine is not part of this. Just kidding, I lied. I apologize. Cool. Okay, so O3 is my reactant and O2 is my product. Intermediates. So what's getting produced and then getting crossed out. So OCl is getting produced and then it's getting used up. So OCl is my intermediate. Oh, look, I color coded it for you as orange. And then my catalyst, something that's at the beginning and something that's at the end. Well, chlorine was at the beginning and chlorine was at the end. And so therefore it must have been the catalyst. It was used just to get the reaction going. Lovely. And then my overall reaction, so I want to count everything up. I've got 2 ozones produces 1, 2, 3 oxygens. Oh, forgot the 3. Right? This is our ozone layer, right? It protects us, our atmosphere. And when we were using all those chlorophylls or those chlorines in our hairspray, they were going up to the ozone layer and breaking it down. So they were just a catalyst to breaking down the ozone layer into oxygen, which is great. We like oxygen and all, but we also like our ozone layer to protect us. So there you have it. Real life scenario, the ozone layer breaking down because of people using hairspray in the 70s and many other reasons, but that's one of them. Cool. So an elementary step is an elementary step that is the slow step. So now we want to figure out how is this going to help us figure out the rate of the reaction, right? We can figure out the overall reaction, but how do I know if it's going to be a fast reaction, a slow reaction, what's going on? So we're looking for the elementary step that is the slowest. The slowest step is the rate determining step. Determining step. Okay, so if you think about, you guys don't have a Cold Stone here. What's a good example? Subway. There you go. Or Chipotle. Let's go Chipotle. So you go to Chipotle and you've got the cashier and you've got the person who heats up your burrito, and then you've got the person who puts all the ingredients on it, and then the person who wraps it. Okay, so we've got our tortilla person, and we have the person who puts the food on your tortilla. And then, so there's step 1, you got to get your tortilla, you get the food on your tortilla, and then 3, you got to pay. Okay, so there's a 3-step process. You're interacting with 3 humans in order to get your food. Okay, so the rate determining step is always determined by the slowest step, right? You want your burrito, you're hungry. Well, if the person who is trying to heat up your burrito is their machine is like having problems and it's taking extra long for it to heat up the tortilla, that is going to be the rate determining step. That is going to slow down the entire reaction, right? If the person who is putting the food on the burrito, it has to stop and tie their shoe, and then their best friend is in the back, so they keep talking to them, and they're just taking forever, right? To like, you're like, hello, cheese, I want cheese. They're taking forever. They are the rate determining step. They are slowing down your entire process. Or maybe this person here, they've forgotten how to do all math, and therefore giving you change is very difficult. So they would be your slowest step. They are your rate determining steps. Your rate is determined by your slowest step, right? You can only be as fast as your slowest person, or whatever that like sports quote is. That applies here in chemistry. Sports, yay. So if we do this reaction, right, we can do these reactions and we can calculate how long it takes to do each of them, and then you can get rates. So instead of giving you actual rates, we kindly just wrote slow and fast. So like, ooh, this one was fast, this one was slow. So we're going to do this if 3 different scenarios were to take place. Let's first look at our reaction here. What is my overall reaction? That usually helps if we know that. So we can write a rate determining step, or rate reaction for each of these. If I go like this, let's see, we've got X getting canceled out. Oh, it's the same one as before. Okay, cool. So A plus 2B plus C produces D plus E. Okay, so same reaction as before. If in scenario 1, so let's say the first experiment takes place and we find that the first step is super slow and then the next 2 are really fast. That means that the rate determining step is coming from this reaction. So my rate is going to be rate is equal to K A B. Because at this point, we only have A and B. Okay? That's all I have to put in here. I don't have any C's yet. Haven't gotten there. And I don't have another B yet either. So just one A and one B. That's all we have in step 1. Now, let's say that in a different scenario, the reaction gave us a fast and slow. So here is my rate. Here is my rate determining step. So I'm going to use this information and the information from step 1, because now I'm slowing down step 1. And I have those things in my reaction. All right, those are in my beaker, right? Those are part of the reaction now. So my rate determining step is going to be B and A. So K, I still have one A, but I now have 2 B's. So that just became second order because it's being used twice. So it is going to change my rate exponentially now because I'm using it multiple times. So as soon as I change B, it's going to change B in step 1, but it's also going to change B in step 2. Right? If I add more concentration of B, it's going to change it twice. So it could exponentially change my reaction rate. And if it's the slowest, we're going to use that as our rate determining step. And the last one is step 3. So let's say in this scenario, the third one is my rate determining step. So that is going to use step 3, but it's also going to affect all the others too. So I need to use A, B, and C in my rate because all of them are being affected. And this is where your overall reaction is helpful because it's the last one. So I have one A, I have 2 B's, that's happening twice in my reaction, so it's going to affect it exponentially. And then C is only in there once. So there you go, only to the first power. Right, this is where like our catalyst and whatnot would be our 0 order, or like the OCl would be your 0 order, right? They're not changing the rate of your reaction. They're intermediates or they're catalysts, and we get to cancel them out of our rate reaction. There we go. So there's our lovely reaction, or our 3 different reactions based off of where you might have the slowest step. So that's how you do that. There is some practice right here for you. So if you'd like to try this by yourself, feel free to pause me and then you can try it by yourself. And then I will go over the answer in just a minute. Okay, I'm going to go over the answer. So if you want to pause me. But if not, here we go. What is the overall reaction, right? So I'm looking on both sides of my arrow. This gets to get canceled out. And that's the only thing that's the same. So I'm left with 2NO plus, sorry, big plus sign, O2 produces 2NO2. And then we're going to determine the rate law. Well, the rate law is always determined by the slowest step. So there's my slowest step. So I'm going to be using everything, right, or my overall equation to help me figure this out. So rate is equal to K. I have NO, and I have 2 of them, times O squared. There you go. Easy money. Cool. So that's how you do that, or that's how you write rate laws using a reaction that has multiple steps or elementary steps. So there you have that. That's how you do that. The last thing we're going to look at real fast is their energy profile. So how does the energy change throughout a reaction? You guys have actually seen these before, and if you look around my room, there's some lovely artwork of art that maybe even you made, or you made something like this. We did like the photosynthesis and the cellular respiration, and we did the bond energy to figure out how much energy it took to make our reactants turn into products. And sometimes they absorb energy and sometimes they release energy, and then that determines if you get an endo or exothermic reaction. So these graphs also help us look at what our reactants and products are doing, and then tell us how much energy is being used and if we have an endo or exothermic reaction. So we have our reactants, we have our products. So lovely, that's already in there. We're looking at energy over the reaction process. So like when I have all reactants, and then when the reaction is over and I have all products. So during this part, it could be multiple steps, right? I could have intermediates all being used up in this time. Intermediates, right? Being produced and used, being produced and used, being produced and used, right? Until finally I've used up all of my intermediates and now I'm just making product. Okay, so your intermediates come in. We know that we need to have enough energy to start the reaction. So sometimes you need to put it in heat. Sometimes you need a catalyst to get the reaction going. But for us to get from the reactants all the way up to where we get to the peak of our reaction, this is our activation energy, EA. It's an E, EA. That stands for activation energy. So how much energy does it get for us to start a reaction and start just getting all of our reactants to turn into products? And then we also know that if we have a delta H here, and this is a delta H that is positive because your products end up with more energy than your reactants, that is considered a endothermic reaction. Why? Because now there is more energy in your products, right? And energy has entered your products, and if energy is entering the system, it's going to feel cold because it's absorbing all of the heat energy, right? So this is where it feels cold because all of the heat has gone into our products. Then we just have this reaction, or this graph, where it shows us the opposite, right? The reactants are on top and the products are on the bottom. This is a negative delta H, so this is an exothermic reaction. There was a lot of energy inside of our reactants. Our products don't need as much energy, so they let that out, and it comes out in the form of heat, so it's exothermic. So there's that for you. But we have some of the same things. We have our intermediates that are taking place throughout the reaction. Intermediates. We have our activation energy. How much energy does it take to get our reactants to start turning into products? So there's our EA. And these reactions just tell us or help us understand, like how the products are turning into reactants and how much energy it's taking, and whether or not a catalyst is needed, or if there's intermediates taking place in there. So there you have that. And then we have catalysts. So catalyst, just a definition because we keep saying the word but we haven't defined it. A catalyst provides like an alternative pathway. So an alternate pathway for the reaction that has a lower activation energy right? So what do we mean by that? We're trying to get our reactants to turn into products. We've found something else that's going to help them get there, and it's going to help them get there with less energy. So lower activation energy, right? That's EA. So if I were to use a catalyst let's do it in like a different color, maybe orange. Use a catalyst in this reaction up here. My EA, my activation energy, this lump is going to go down. So I might start with the same amount of reactants, but now, and my products are still going to end in the same spot, my EA is smaller, right? So I'm lowering my hump. I don't need as much energy to get my reactants to turn into products. Okay, so activation energy is helping us get there with less energy. And oftentimes that is seen as faster, right? That's why it's part of kinetics. It's making you go faster. And this is the same thing, right? The same little picture. I just made mine up on the graph because I wanted to. Okay, that's all I have for you. You have a targeted check that you can work on. You have your lab that you can finish. And you also have your presentation for your final that you can finish. You can do all of this while you're listening to Lainey, Lou, and the Bird Dogs. Right, I'll attach a little link for you so you can listen to some of the music. You can pretend you're at this concert with me. So much fun. Cool. Have a great day. I will see you guys on Monday. Enjoy your weekend and get everything done and turned into me. Bye.